share with people. Okay, so hi guys. So we are discussing here in office hours LP spaces with Miguel Mascoro. So what is happening here is that what is interesting on these LP spaces is that you are integrating over X, right?
Mm-hmm.
But look at F goes from X to the real numbers.
Yeah.
So when you integrate these, and notice mu also goes to the real numbers. So at the end, this integral looks funny because it has this X, but it's really a real integral. Okay.
Mm-hmm.
So just the notation is as like weird, but the integral is just like, well, not exactly like calculus integral, because if mu of x is the Lebesgue measure, is practically the same that calculus one. But mu could be something else. For example, in the exam we have, this could be a probability space. So x could be the events of an experiment. M could be the sigma algebra, and mu could be the probability measure, the probability. So basically, what I'm saying is, we could, to the exercise from the exam, we could make an LSP space of that. Okay?
Mm-hmm.
That's really what it's saying. And so what is it? What is an LP? In LP are all the functions that are, let's say, P integrable. They usually call it P summable or something. It means this integral is less than infinity. And the norm is this. Let's see what else. Let's see what else is in the next page. So since this is a norm, you guys learning in analysis one that if you have a norm, you can make a metric. Okay. So because you have a norm, you can do more. You can define a metric, but this is the norm. So it has all these properties that will make a norm, and with the norm you can make a metric. And then that's what you have. You can make balls. You can make balls. So this LP space is a metric space. So when P equals 2, that's when you say the functions are square integrable, and that's what the people use now in basically statistics, right? In statistics and physics.
Mm-hmm.
So before in physics, in classical physics, you used to use vector spaces like R1, R2, R3. This space L2 is the quantum mechanics space. Okay, so that's why this is so important. Okay, and now the imaginary. Don't worry about the imaginary part. But so question. Do you have a question, Miguel?
Yeah, my next question would be related to the dominated convergence theorem.
Mm-hmm. Okay, but so let me make something here, since I have this. I can make some. Oh no, maybe I can do it here. Let me make something more about. So you wanna understand, if you want to understand. Oh no, it's not giving me.
Mm-hmm.
I'm gonna say it again. So the most important one is L2. So this is the set of functions such that it's enough to just to say that the integral of f squared
Mhm.
the mu or dx. I mean, at the end, it really you can think first in dx, like just to make your life easier for physics. It's less than infinity. Okay. So why is this important? So if you remember from your statistics class, this is one of very famous function is the Gaussian function.
Mhm.
And it's just the heat kernel of the heat equation. Okay. So and the main application of all these LP spaces is the applications to solve or partial differential equations. Okay. And why? Because they are connected to real life problems. So why do we want LP spaces? So remember your linear algebra, you saw vector spaces, right? So vector spaces where the real numbers, right, are n. So that's why you take your linear algebra in graduate school. You learn vector spaces, and usually they're finite dimensional.
Yeah.
So what happened is that in partial differential equations, this is not enough. So this is good for ordinary differential equations. When you have a system of equations, ordinary differential equations, like for example, COVID-19 is modeled by an ordinary differential equation. Or so susceptible, infected, recover. So you have three equations. And they're coupled, and they pretty much look like one goes like this. That's the recover. This is the wave of infected. And this is the other one is gonna be the people that it gets infected. Well, we can eliminate the last one. It's the complement of the other two. Okay. So you can do a lot of mathematics just with an ordinary differential equation. But for when you have systems, or a partial differential equation it can be written on an infinite ordinary differential equation system, infinite. So it's not enough to do vectors here. So here is enough to do, let me see. I want to draw, and I'm going to use, let's see. Okay. It's not enough to do vector, right? So remember we do like this. Okay, so a vector is B1, let's say R2. This is B1, B2. So that's B1 and B2. But I did talk about this in my lectures. But it's good that to clarify. So what is modeling this L2? What is this L2 is important? So part of it, why it get popular is because this is gonna be a vector space. So you remember, Miguel, what is the main property of a vector space? Or not the main, but one of the what a vector space is important. One quality of the vector spaces.
The fact that it's closed under addition, probably.
Yeah, that's the definition. Yeah. What else? Close. What do you say? Close under?
closed under addition, under scalar multiplication.
Scalar multiplication, not division.
Right.
No, scalar multiplication, what else? You can add, you can subtract, right?
Mm-hmm.
What else can you do in a vector space?
Add, subtract, multiply.
Can you multiply times what?
Times scalars.
Yeah, can you multiply two vectors?
Not necessarily. I mean, there won't.
No, you cannot. But you have something else. What is what you have you can do? In a vector space, what is this the closest thing to a product of two vectors?
The dot product, the inner
The
product.
dot product, there you go. So the dot product, you get two vectors, x and y. And you know, this is funny, it's, you know, it's the cosine, you know, you have the vector x, you have the vector y, you have the angle, and then the vector is something like the cosine of the angle divided by the norm of each of those two, right?
Mm-hmm.
If I'm not wrong. Cosine of the angle, we can look, because I don't remember exactly the, yeah. And now I wanna get down. So sorry, I'm gonna have to stop sharing. Let me go down here. Oh. Okay. Okay, sorry, I know what is. So I usually don't use this one, but okay, so erase everything. Okay, so we can look here. So let me use mouse, but I think it's just that. So the inner product is the x and y. Is the cosine of the angle divided by the norms. The product of the norms. And we can verify. But so maybe this is not exact, but it's basically the idea. So you got the angle, and you got this, the norm of this guy divided by this norm, and this. So do you remember why this cosine of theta help us to figure it out?
The cosine?
Yeah, but what is the main property of the inner product? It helps us to figure out when two vectors are
Orthogonal.
orthogonal. There you go. I like to talk to you because you know all the answers. So it's good to make a video with you. So this, if the vectors are orthogonal, the inner product is 0.
Right.
Right? So, and that's exactly what is gonna happen. But you know, when you have L2, you have two functions, f and g. So how will you define an inner product of two functions if you cannot see that orthogonal, right? You can make two vectors and you say like, how can I figure out that they're orthogonal? It does even make sense. And yes, it makes sense. So the inner product definition is the integral of f times g.
Mm-hmm.
Let's call it dx. Our measure is the Lebesgue measure. So that's everything is beautiful. So if f is g, so I'll get inner product of f is the norm of f of square, the norm of f, right?
Mm-hmm.
So the inner product of f with f is just my norm, my my integral, whatever, but it's just basically my norm of f squared, because it will be the integral of f of squared dx. Okay.
Mhm.
So it's an exercise to prove that L2 is an inner product with the, I'm sorry, that this is an inner product for L2. So what it helps you is that it's going to determine when two functions are orthogonal.
Mhm.
So, and so what? So what else can you do with L2? So once you have L2, guess what? You know where I'm going? What do you think I'm gonna, what could be the main application of this idea? This is a long shot, but you know, since you took my REU, you might have some idea. What could be the main applications of inner product of L2? No idea?
I'm sorry, I don't have an idea.
No, that's fine. That's fine. So Fourier series,
Okay.
because if you make x equal sign and you make a let's make it better. You know, let's go to here. Yeah, let me open a book, because one of my books does a really good job, and it's a undergraduate book. So let me open a book. So that's this book. It has a great job. Does a great job explaining this Fourier series in a very easy way. So we go all the way to primary problem, special science, Stolliver problem, Fourier series. I think orthogonal functions. Let me raise this. So this book, you know, is an undergraduate book, but they really do a great job. That's probably why it's so popular. So let me stop this thing. Okay. So you see in the book, they right away, they define the inner product of a vector space, R3, right? So those are my properties of a vector space. Everybody knows this. But now look at the inner product of two functions is this. And notice they're not talking about Lebesgue measure or anything, because this is basically Lebesgue measure. When you are, you saw in my last video that the final integral between a and b of dx is exactly the Lebesgue, the same thing that if my Lebesgue measure is, if I use in my Lebesgue measure, right? So something beautiful here is that you can define orthogonality of two functions. Mm-hmm. They are zero. And now you can prove, for example, that x squared and x cubed, they are zero in between minus 1 and 1. Okay, they are orthogonal. And the x squared and x4, that are not orthogonal. But this is really what is important, the orthonormal sets. And look at this beauty. So we wanna make a base, just like we have for what is the base for R3? Remember what is the base for R3?
The bases?
The basis. Yeah, what is the basis for R3?
Well, the standard one is 1 0 0 0 1 0 and 0 0 1.
There you go. So question for you. What could be a basis for L2?
Um,
Like no idea because
probably an
uh-huh.
orthonormal set, or just
Exactly, that's what it's gonna be. It's gonna be orthonormal set, but which one? So this example here is showing me. So probably the guess of any student will be polynomials. But this example here is showing that polynomials are not that good. That is crazy because Taylor's theorem is just about polynomials. Remember Taylor's theorem?
Yeah.
Taylor expansion?
Yes, I do.
Mm-hmm. So that's kind of a break your heart, but then we have something new. Look at this base: 1 cosine of s, cosine of 2s, cosine 3x, and so on. So this is the cosine Fourier, the cosine, a cosine base, let's say, but this is gonna become the cosine Fourier series. So it happens that these two, you got cosine of x with cosine 2x, the integral of this guy is going to be 0, so they're orthogonal. So I wanted to cover this, but you know, I didn't want to put more stuff into the class. I think people have already difficult times, so I didn't want to put more stuff. But this is really what I wanted to finish with, and ask and the final probably Fourier series and things like that. But I don't want to push so hard right now under the current situation we have with the pandemic and everything. But you see, if you take any cosine of mx, cosine of nx, they are gonna be orthogonal. And the next part, I love it. So let's say, and let me go back to my word right here. Let's say I want to write. So you said, okay, all this work. Okay, so I believe you. The cosines, cosine x, cosine 2x. Let me see. Can I write this here? The 1 cosine x, cosine 2x, etc. are an orthonormal set. And the question is, this is an orthogonal set of R2. So this is a subset of L2. Let's say L2 like this. Okay. So the question is, let's say, I don't know if we're saying minus 1, 1. I think we're saying minus 1, 1. This is your x, the x you were asking. Okay. In this case, you are working in an interval. So
I believe the interval was from negative pi to pi.
Oh, okay. Well, yeah, it changes. In some sometimes they call it minus LL because you can also use a scale.
Okay.
But yeah, we can use that one. So that's your. So yeah. So the problem of this measure theory is that you talk so abstract because you think people know these basic examples, and that's not really true in general. So. So let me take an f of x in L2. Let's say I feel lucky. Let's say that this f of x I think is good enough, and I want to write f of x as a linear combination an on my cosine of nx. This is a total valid question. What can I do with this orthonormal set? So let's call it n equals, you want n equals 0 to infinity. Can I write that? Why? Because I know that by Taylor series, so recall Taylor, I know that I can write a function of expansion, right? So by Taylor, this is like x minus a to the n and then the n derivative evaluated at a divided by n factorial, something like that, right?
Yes, I believe that's correct.
So this is Taylor. So this, if my f is differentiable, I can write it like that. But L2 is not necessarily differentiable. Look at this. This is an L2 function.
Mm.
And that function is not differentiable.
Yeah.
So more than that, so let's make it like that, like a signal. Like for electrical engineers. Let's make it like a signal, a periodic signal. That is not differentiable. How could I approximate this function, even if it's from minus infinity and infinity? How could I write this function? Let's say this is f. How could I write this function? Clearly, Taylor doesn't work here because this is not differentiable.
Yeah.
So how could I do this? Can I do this with my new base? And the answer is gonna be yes. So I ask you, let me and ask you, everybody that's watching this video. So let me make a quiz. How would you find a sub m? So, or better, the a sub n, a sub 3. Let me be very specific because, sometimes the problem is we talk too general and we don't concrete. How do you find a sub 3? And I give you a hint. Use inner product. How could you use inner product to find your a sub 3?
Do you want me to say it?
Yeah.
Okay, we could probably take the integral, the inner product, and make it so use the orthogonality of the cosines, so that we're only left with cosine of 3x, because if we're only left with cosine of 3x, we're gonna be left with a3.
Okay, so
we're gonna take the integral from, in this case, negative pi to pi of f of x times cosine of 3x, I believe. Dx.
Okay, perfect. Yes, that's exactly correct. So for people watching, we didn't agree to do this together. So it's totally live. So yeah, so he's correct. So I want to eliminate. I only want a3 live. So I just want a3. So he's saying make f of x, multiply everything times cosine of 3x. Cosine of 3x. Both sides, right?
Mm-hmm.
And of course, what are the issues here? And here you're gonna see the application of our Lebesgue increasing dominated convergence theorem and stuff. So I'm gonna multiply times cosine of 3. So I got sum n equals 0 to infinity. And I multiply everything times cosine of 3 of x, right?
Yeah.
And now he said, let's integrate between minus pi and pi, both sides. And integrate here, minus pi and pi. Okay, so now what?
Well, we can, instead of writing from n equals 0 to infinity, we can take the limit as, for example, as t goes to infinity, and get the sum from n equals 0 to t. And then we can apply our the Lebesgue domination theorem.
So basically, we had to use analysis 2. This class, analysis 2, to justify that interchange the integral with the sum. So we changed, let's say, this is the sum. Now we have the integral.
Mm-hmm.
And so we will have to argue, and that's a whole argument from n equals 0 to infinity. But as you said you can make the limit, and you can call this from k, and then you call the infinity, instead of calling infinity, you call it k. So this guy k. Sorry. Call it k. You call it integral here. Okay? So you're justifying interchange the integral with the limit. And then once you interchange, you just integrate one by one. So you have an cosine nx cosine 3x. Well, let me erase here and do it on the top, because this is important. So this is gonna be, let me close this so you don't get confused. This is something else, okay? So this is equal here. So this is
so it's going to be the sum. And we can even take the an out, so that we just have the integral of cosine.
So let's make the sum an out, n equals to 0 to infinity of the integral of cosine nx times cosine 3x. And dx between minus pi and pi. And now what?
And now wherever n is not equal to 3, they're going to be 0.
Yeah, correct.
So we're going to be left with
exactly
a3 times the integral from negative pi to pi of cosine of 3x squared.
So this guy, so everything else is going to cancel. Whatever is not 3 cancel, because it's orthogonal. The integral is going to be 0.
Right.
But so we have only left with a3 and the integral of cosine 3x times cosine 3x squared minus pi. So what is that? That is the norm, or cosine 3x squared in L2, no?
Yes.
And it's a square because I don't have a square root, so let me put the square. So therefore, this is my A3. So to conclude, my A3, and this is that's what you learn in Fourier series, okay? So to conclude, my A3, so let me see what I can write. Let me erase my A3 is this integral over here, the integral of f of x times cosine of 3x dx divided by the norm of cosine of 3x. In this in this norm. Okay. And this is 3, well, you just change 3 by n, and you have the same thing for all those guys. So this is your formula. 3. So this is 3.
Yeah.
This is 3. Sorry, n. So let me close my door because the kids are making noise. Cosine nx, and this is n. Okay. And this is your formula or Fourier series. So give me a second, I close the door.
Yeah.
So let's go back to the book. So I'm gonna have to erase all this. So that's the formula.
And just to be clear, we could change that 3 to n because we didn't use the fact that it was A3. This applies for any n, right?
Exactly, yeah. So this is A sub n, right? That's what I put, A sub n. Yes or no?
Yeah. It makes sense.
Okay. So let me see if I can change my screen. Okay. I need to erase all this. Oh no, but that's not what I need to. So the book, I didn't like how the book does Fourier series here because it's just too graduate. Like they assume students know all this, and they make it very very kind of hard. This is a beautiful, easy topic. They make it hard, so that's what I'm using here. My classical book of differential equations. So that's what they do here. You see, they have some norms. This is the orthonormal set, and then they normalize it to make sure that this is gonna be 1. And this is vector analogy. That's actually I got I think I imagine I got this from here. So you see, you do the inner product, and that's what you get. Okay. And this orthogonal series expansion. So now you get another function, and you do the same thing with other bases. It doesn't have to be only cosines. So you can have sines, and I'm gonna show you more complete sets. So that's what is calling next Fourier series. So this is the classical Fourier. This is called classical Fourier cosine series. Although no, this is Fourier series complete. So you have a combination of cosine and sine. And that way, this is your trigonometric Fourier series. You have to prove the inner product is gonna be, same thing, but now you have to do it twice with 2 integrals. And then that's your Fourier series. And that's the definition. You see, Fourier series, a Fourier series of function f is defined on an interval of minus pp, but it's because it's periodic. So, and this is your definition. That's how you can extend your function instead of a Taylor series as this one, because this function, look at it, it's not saying it's derivative, it's differentiable. Taylor has to be differentiable. So that's why the applications is in signals. And then some convergence that then you can see now. That's the convergence of the Fourier series. So you see, this is what they wanted to converge to. And this is just S3, SA, S15, S3, S15. So they want to approach to these lines. See, the signal is this line, horizontal, this diagonal, horizontal.
Yeah.
And that's how it's going to converge. And what is convergent? So this book doesn't say what is convergent. It's convergent because analysis too. Okay. So let me see what else here. So Fourier cosine series. This is more about convergence. More examples. More examples of convergence, but they don't. So the basics, the mathematical basis of this Fourier series is what we're doing, analysis too. And then I think the next is the soluble problem that it just gives you different bases. Okay. So it turns out that we are working with cosine and sines because we are in this model. If you have another differential equation associated, you will have other bases. And that's how it gets good. Okay, let me stop this video here.